In the study of spectroscopy, it is required to know the different energy levels of a molecule and their spectra in spectroscopy due to observing energy from EMR. Spectroscopy is the branch of science that deals with the study of the interaction of electromagnetic radiation with matter. Because of such interaction, the matter absorbs or emits the energy in discrete amounts called quanta, and is depicted as a spectrum in spectroscopy. By studying this spectra, we can find out the different properties of a matter. There are various energy levels in a molecule, but among them, the three energy levels are very prominent, and they are electronic energy level, vibrational energy level, and rotational energy level. Now, if I give a brief description of them, you will be able to feel them properly. Electronic energy. Electronic energy is the energy associated with electrons. There are several molecular orbitals in a molecule. These molecular orbitals can be bonding or anti-bonding. The electron can occupy any of these orbitals depending on the energy it has. The gaps between the electronic energy levels fall in the UV visible region in the EM spectrum, that is from 100 nanometer to 700 nanometer. Vibrational energy. Each such electronic state contains a range of vibrational levels equal to 0, 1 to 3, etc. The atom in a molecule can vibrate by keeping the position of its center of mass constant. Energy associated with this type of vibration is called vibrational energy. The gaps between the vibrational energy levels fall in the IR region of EM spectrum, that is from 0.75 micrometer to 1000 micrometer. Rotational energy. Again, each vibrational level comprises a fine structure of rotational energy levels are equal 0, 1, 2, 3, etc. If a molecule rotates in space about an axis passing through its center of mass, then the energy associated with that rotation is called rotational energy. The energy gaps between the rotational energy levels fall in the microwave region of the EM spectrum, that is from 1 millimeter to 30 centimeter. Beside those energies, there are other energies in a molecule, such as translational energy due to the translation of molecules and nuclear energy due to the nuclear motion, but these energies do not provide any useful information about the electronic structures and chemical properties of the molecules, so they are omitted in the quantization of the molecular energies in spectroscopy. Therefore, the total energy of a molecule is the summation of electronic energy, vibrational energy, and rotational energy. And obviously, electronic energy is greater than vibrational energy is greater than rotational energy. Now, to understand how the spectrum is formed, we have to discuss the energy gaps between them and finally merge them in the way shown in the diagram. So, let's say the energy gap between two rotational energy levels is too small or less than the energy gap between two vibrational or electronic energy levels, because each vibrational energy level contains several rotational energy levels, so the energy gap between two vibrational energy levels is greater than the energy gaps between two rotational energy levels. In the same way, the energy gap between two electronic energy levels is greater than the energy gap between two vibrational energy levels, as well as the energy gap between two rotational energy levels. Further, the energy gap between two rotational energy is increasing, that is R1 minus R0 is less than R2 minus R1 is less than R3 minus R2, and so forth. You can see the gap is expanding from lower to upper, right? On the contrary, the energy gap between vibrational energy levels and electronic energy levels is decreasing, that is V1 minus V0 is greater than V2 minus V1 is greater than V3 minus V2, and so forth. The same is true for electronic energy level, that is E1 minus E0 is greater than E2 minus E1 is greater than E3 minus E2, and so on. Now, to understand the spectra, we have merged the energy levels in one place. You can see is electronic energy level contains a range of vibrational energy levels. The first electronic energy level contains the vibrational levels as V double prime equal to 0, V double prime equal to 1, V double prime equal to 2, V double prime equal to 3, and so on. The second electronic energy level is the energy level between E equal to 1 and E equal to 2. Here the vibrational energy level is depicted as V single prime equal to 0, V single prime equal to 1, V single prime equal to 2, V single prime equal to 3, v single prime equal to n, etc. It is a convention to use double prime to indicate the lower energy state and single prime to indicate the higher energy state. Somewhere you can see to use a star to indicate a higher energy state, such as here. And again, each vibrational level contains a range of rotational energy levels, which is denoted as r double prime equal to 0, r double prime equal to 1, r double prime equal to 2, r double prime equal to 3, r double prime equal to 1. We use r double prime to indicate that the rotational energy belongs to the energy levels between equal to 0 and equal to 1, and r single prime to indicate that the rotational energies belongs to the electronic energy state between equal to 1 and equal to 2. Now the picture is also clear to you that each electronic level contains a range of vibrational levels, and each vibrational level contains a range of rotational levels. One more thing, the energy between equal to 0, the lowest electronic energy level, and v equal to 0, the lowest vibrational energy level, is called 0 point energy. Now I will describe different kinds of spectra relating to different kinds of energy transitions. The first one is rotational spectra. If the energy absorbed by the molecule is so low that it can cause the transition from one rotational energy level to another rotational energy level within the same vibrational energy level, then the result is called rotational spectra or pure rotational spectra, because here only the rotational transition take place. Here the same vibrational level means the space between the vibrational state v equal to 0 to v equal to 1, and these spectra are like that. Vibrational spectra. If the energy absorbed by the molecule is sufficient to cause a transition from one vibrational energy level to another vibrational energy level within the same electronic energy level, the result obtained is called vibrational spectra. Actually, simultaneously it creates vibrational and rotational spectra, because you can see that it covers both vibrational and rotational energy levels at the same time. And the spectra are like that in some special cases. These spectra are for rotation, and these spectra are for vibration. These are for carbon dioxide, these are for nitrous oxide, and these are for acetylene. Electronic spectra. If the exciting energy is so high that it can cause the transition from one electronic energy level to another electronic energy level, then the result obtained is called electronic spectra. Along with it, vibrational and rotational spectra can also be formed due to vibrational and rotational transitions, and some of the electronic spectra are like that. Moreover, there are 4 types of electronic transitions, such as sigma to sigma transitions, into sigma transitions, etc., which will be discussed in the following videos in details. Now finally, I will discuss the intensity versus wavelength graph. The picture here shows the intensity versus wavelength graph of a spectrum of a typical excited sample by absorbing energy from EMR. Here, for the different discrete and close energy gaps of these different energy levels of the sample absorbs different energies which match with those energy gaps from EM radiation and gives a continuous broad absorption band like this. Basically, this band is in the merged form of those previously discussed different spectra of different energy levels. It is a typical or schematic absorption spectra, and it shows that in the initial wavelength the sample absorbs less energy, in the middle range wavelength the sample absorbs the maximum energy from the radiation, and in the far wavelength it absorbs the less amount of energy from the EM radiation. And again, when this excited sample emits certain radiation and come to the ground state, then the spectra found by the spectrometer is called emission spectra. Again, as I discussed before, the different energy gap and the region in the EM spectrum, that is the energy gap of rotational energy level following the microwave region which has the large wavelength, for example the radio wave, and the energy gap of vibrational energy level following the infrared region which has the medium wavelength, and the energy gap of electronic energy level following the UV visible region which has the minimum wavelength. So by observations, we can say that here for the increasing wavelength, these spectra are created by the energy of vibrational and rotational transitions, and for decreasing wavelength, these spectra are created by mostly the energy of electronic transitions. So here this portion is by rotational transition, this portion is by electronic transition, and in this portion here the 3 transitions take place, that is by rotational, vibrational and electronic transition. Because in the case of electronic transition for complex molecule. Basically, the three transitions take place simultaneously: rotational, vibrational, and electronic transition. In the case of vibrational transition, the two transitions take place simultaneously, the vibrational and rotational transition. So here the sample absorbs the maximum energy by maximum transitions. Thank you very much. See you in the next videos. Till then, stay well.